Hello and welcome. In this notebook, we continue learning PyTorch. In this course, we learn transfer learning, custom loss functions, advanced models, and debugging and visualization. If you find this video useful, please consider like, subscribe, and share video with others. Transfer learning. Using pre-trained models from torchvision.models. In this slide, we will learn how to use pre-trained models from the module called torchvision.models. Transfer learning helps us use existing knowledge from large datasets like ImageNet without training a model from scratch. This saves time and resources. Torchvision.models provides several well-known deep learning models such as ResNet, VGG, DenseNet, and MobileNet. To use a pre-trained model, you simply set the argument called pretrained equals true. This loads the model with learned weights. These models can be used either for extracting features or for fine-tuning on a new task. We will explore these two methods in the next slides. First, we import Torch. Next, we import models from torchvision.models. Then we load a pre-trained model using the following line. Model equals models.resnet18 with the argument pretrained set to true. This downloads the ResNet18 model that has been trained on the ImageNet dataset. Next, we print the model using print, open parenthesis, model, close parenthesis. This displays the full model architecture. The output includes layers like conv2d, with input channels equal to 3, output channels equal to 64, kernel size 7 by 7, stride 2, and padding 3. There are also batch normalization layers and ReLU activations. At the end, the model has a fully connected layer. This layer is a linear layer with 512 input features and 1,000 output features, representing the 1,000 classes of ImageNet. Feature extraction. In this slide, we explain feature extraction. Feature extraction means we freeze the weights of the pre-trained model. This allows the model to use the learned features from a large dataset like ImageNet. We do not change the convolutional layers. Instead, we replace the final classifier layer with a new one for our own task. This method trains quickly and is very useful when we have limited data. Because most of the model is frozen, we also reduce the chance of overfitting. We start by importing Torch, neural network as NN, and models from torchvision.models. We load a pre-trained ResNet18 model by setting pretrained equal to true. To freeze the existing layers, we loop through all model parameters. For each parameter, we set requires_grad to false. Next, we replace the final fully connected layer using model.fc equals nn.linear with 512 input features and 2 output classes. Finally, we check if the new layer will be trained. We print whether requires_grad is true for model.fc weights. The output confirms that only the classifier layer is trainable. Fine-tuning. In this slide, we explain the concept of fine-tuning. Fine-tuning means we allow the pre-trained model to keep learning. We unfreeze some or all of its layers so they can be updated on our custom dataset. This method is useful when our new task is very different from the original task the model was trained on. Fine-tuning usually gives better accuracy, but it takes longer to train and works best with more training data. We load a pre-trained ResNet18 model with pretrained set to true. In fine-tuning, we allow the whole model to keep learning. By default, all layers are trainable, so we do not need to set requires_grad manually, unless they were frozen earlier. We replace the final classifier layer using model.fc equals nn.linear with 512 input features and 2 output classes. Finally, we print whether an early layer, such as model.conv1, will be updated. The result shows that requires_grad is true. This confirms that the entire model, including the feature extractor, will be trained. Freezing layers and adapting classifiers. In this page, we cover freezing layers and adapting classifiers. Instead of freezing the whole model or training all layers, we can choose a hybrid approach. We freeze the early layers to keep the general features, like edges and shapes. Then, we unfreeze the deeper layers, which capture more task-specific features. This lets the model adapt to our new task while training faster than full fine-tuning. We also replace the classifier layer to match the number of output classes in our dataset. This method provides a good balance between training speed and accuracy. We begin by importing Torch, neural network as NN, and models from torchvision.models. We load a pre-trained ResNet 18 model with pretrained set to true. Now we freeze only the early layers of the model. These include Con1, the very first convolutional layer, BN1, the first batch normalization layer, Layer 1, the first residual block. We loop through all named parameters of the model. If the name starts with Con1, BN1, or Layer 1, we set requires grad to false. The function starts with checks that the name begins with those exact terms, so we do not accidentally match deeper layers that also contain the text Con1. This leaves the deeper layers, such as Layer 2, Layer 3, and Layer 4, still trainable. They will adapt to the specific features in your new dataset. Next, we replace the classifier. We assign model.fc to a new linear layer that outputs 5 classes. This matches our custom classification task. Finally, we print whether conv1 is trainable. It should return false, confirming that it's frozen. Then we check a deeper layer, like the first convolution inside Layer 2. It returns true, which means it will be updated during training. This confirms that only early layers are frozen, while deeper layers and the classifier are trainable. Custom loss functions. Writing custom loss functions. In this page, we explain how to write custom loss functions in PyTorch. A loss function measures how far the model's predictions are from the actual targets. This value guides the model during training. It tells the optimizer what to minimize. In PyTorch, we can write custom loss functions by creating a class that subclasses neural network.module. Inside that class, we define a forward method to calculate the loss. Custom loss functions are useful when the built-in ones, like cross-entropy or mean-squared error, do not fit your problem well. You can use them when you have special constraints, non-standard metrics, or multiple objectives. We define a new class called custom L1 loss. This class subclasses nn.module, which means it behaves like any other PyTorch layer or loss function. Inside the constructor, we accept a scale factor. This lets us control how strongly the loss influences training. We store it as self.scale. In the forward method, we take the output from the model and the ground truth target. We compute the L1 loss by subtracting the target from the output, taking the absolute value, and calculating the mean. Then we multiply the result by the scale factor. Next, we create an instance of the custom loss function by passing scale equals 0.5. We create a sample output and target tensor. Then we compute the loss using our custom function. Finally, we print the loss using loss.item. The printed value shows the average scaled L1 difference between the predictions and targets. Combining multiple parts in loss function. In this slide, we show how to write a custom loss function that combines multiple parts. This is useful in multitask learning, where the model has more than one objective. It's also helpful when we want to add regularization or other constraints to the training process. Each loss term is calculated separately and then combined into a total loss. We can apply weights to each term to control how much they influence the final result. This gives us flexibility to guide training toward multiple goals. We start by importing torch and neural network as NN. We define a new class called combined loss. Its subclass is NN.module, so we can use it like any other loss function in PyTorch. In the constructor, we create two parts, a mean squared error loss stored as self.mse, a scaling factor alpha, which controls how much the second loss term contributes. In the forward method, we compute two values. First, loss_main, which is the mean squared error between the output and the target. This is the standard loss we want to minimize. Second, loss_reg, which is the mean of the absolute values of the output. This acts like L1 regularization and helps keep the model's outputs small or sparse. We then combine the two parts. We return the sum of the main loss and alpha times the regularization loss. Next, we create an instance of the custom loss with alpha equal to 0.2. Then we define a sample output and a target tensor. Finally, we compute and print the total loss. The printed result includes both the mean squared error and the scaled regularization term. Advanced models. Attention mechanisms. In this page, we introduce attention mechanisms. Attention is a powerful concept in deep learning that allows models to dynamically focus on the most relevant parts of the input when making a prediction. Instead of processing every input token, word, or pixel with equal importance, attention enables the model to assign different weights to different parts of the input based on their contextual relevance. This mechanism helps the model selectively concentrate on the segments of data that contribute the most useful information for the task at hand, while minimizing the influence of less relevant or redundant parts. For example, in machine translation, attention allows the model to align words between the source and target languages, focusing on appropriate source words when generating each word in the translation. In text summarization, it helps highlight the most informative parts of a long document. In image captioning, attention can guide the model to look at the specific regions of an image that are relevant to the words it's generating. There are several types of attention mechanisms, including soft attention, which is differentiable and trainable via backpropagation, and self-attention, which allows the model to consider the relationships between all parts of the input, even when they are far apart. Self-attention is a key building block of transformer architectures. Attention mechanisms have become foundational in both natural language processing, NLP, and computer vision, CV. In NLP, they are central to models like BERT, GPT, and the transformer. In vision, attention is used in vision transformers, object detection, and image classification tasks. Overall, attention significantly improves the model's ability to handle complex, structured data by enabling it to prioritize contextually important information, leading to more accurate and interpretable predictions. First, what are query, key, and value in attention mechanism? Let's say we are building a translation model. The model reads an English sentence like, "The cat sat on the mat," and we want it to translate this into French. When the model is trying to decide how to translate the word sat, it needs to know which other words in the sentence are most important. That's where attention comes in. Here's how it works. The model turns the word sat into a query. It's like asking, which other words in the sentence help me understand what sat means here? All the words in the input sentence, like the, cat, on, and so on, are turned into keys and values. Each word has a key that describes what it offers, and a value that holds its actual meaning. The query is compared with each key. If the key and the query are similar, it means that word is useful. The attention score will be high. Then, the model grabs the values of the most relevant words and combines them to help translate sat, more accurately. So in short, query, the word being processed, the question. Keys, all other words, what each one offers. Values, the useful meaning to bring forward. This works the same way in vision tasks too. For example, when processing an image, the model might ask, which part of the image helps me detect a dog's face? That becomes the query, and it will attend to the important parts of the image using keys and values. Second, how are Q, K, and V trained? The good news is, we don't create query, key, and value vectors by hand. The model learns to generate them using small neural networks called linear layers. Here's what happens during training. First, each input, like a word or a pixel, goes through 3 different layers. One layer makes the query, one makes the key, and one makes the value. These layers have learnable weights, just like any other part of a neural network. During training, the model makes a prediction, calculates a loss, and backpropagates the error. That loss flows all the way back through the attention mechanism and updates the weights inside the Q, K, and V layers. So the model gradually gets better at asking useful questions, comparing correctly, and focusing on the right information. You don't have to manually design the queries, keys, or values. The model learns them and improves them automatically, just like it learns to recognize cats or translate sentences. In this example, we are going to walk through how scaled dot product attention works. This is the core operation that powers attention mechanisms in deep learning. We begin by defining 3 things: a query vector, a key matrix, and a value matrix. Let's first understand what these terms mean. The query is like a question. It represents the information the model is trying to find or focus on. For example, in language translation, the query might represent the word the model is currently generating. The keys are like labels or identifiers for the available input information. Each key represents part of the input, like a word or feature, and is used to compare against the query. The model uses the query to ask, which of these keys is most relevant to me right now? The values are the actual information the model wants to use. Once the model decides which key is most relevant, it selects the corresponding value. So, the keys help choose where to look, and the values provide what to take from that location. In code, we create a query vector labeled capital Q with values 1.0 and 0.0. A key matrix labeled capital K, which contains 2 key vectors, and a value matrix labeled capital V, which also contains 2 value vectors. Each vector has 2 elements, meaning we are working in a 2-dimensional feature space. Next, we compute the similarity between the query and each key. We do this by taking the dot product between the query and the transpose of the key matrix. This gives us a score for each key. A higher score means the key is more similar to the query. In this case, the query matches the first key exactly, so the first score is high. The second key is completely different, so its score is low. Then we scale the scores. We divide each one by the square root of the size of the key vectors, which is 2. This scaling step prevents extremely large values that could make training unstable. After scaling, we apply the softmax function. This converts the scores into attention weights that add up to 1. These weights represent how much attention the model should give to each input position. Finally, we use these attention weights to compute the output. We multiply the weights with the value matrix. This gives us a weighted combination of the values. Since the model gave full attention to the first key, the result closely matches the first value vector. The output is 10, 0, which shows that the model focused entirely on the first piece of input information. This is how attention works. It allows the model to look at all inputs, decide what is important for the current task, and then extract the most useful information from those parts. Transformers. The transformer architecture is the foundation of many powerful models used in natural language processing and computer vision today. Unlike older models like RNNs, which process input tokens one at a time, transformers handle entire sequences in parallel. This makes them faster and also better at capturing long-range relationships. At the heart of the transformer is self-attention, specifically multi-head self-attention. This allows the model to look at every word in the sentence and decide which other words are most relevant, all at once. Each attention head learns to focus on different patterns or types of relationships. For example, one head might look at grammatical rules, while another tracks word order or meaning. To help the model understand the order of the words, transformers also add positional encodings. These are learned or fixed vectors that tell the model where each token is in the sequence. Then, after computing attention, the model passes the result through a feed-forward neural network, which learns richer representations. All of this, attention, position, and feed-forward processing, happens inside each transformer block. Transformers can stack many of these blocks together to build very deep models. This architecture is the backbone behind models like BERT, GPT, T5, and also image-based models like Vision Transformers or VIT. In PyTorch, the basic building blocks for transformers are transformer encoder layer and transformer encoder. You define a single attention layer using transformer encoder layer, and then stack multiple of them using transformer encoder. The input must include positional information. This is important because attention by itself does not understand order. You can add positional encodings manually or use pre-trained embeddings that already include position. Also, be careful about input shape. In PyTorch's transformer layers, the input should be a tensor where the first dimension is the sequence length, the second is the batch size, and the third is the embedding size. This allows the model to process the entire sequence in parallel rather than one step at a time. Transformers are highly efficient and can handle long-range dependencies much better than RNNs or LSTMs. Now, let's move on to the code implementation. We begin by importing Torch and the neural network module. Next, we create a random input tensor named X. It has 10 tokens, one batch, and each token has 32 features. The shape of the input is 10 by 1 by 32, that is, sequence length 10, batch size 1, and embedding dimension 32. We define a transformer encoder layer using transformer encoder layer. The model dimension is set to 32, matching the embedding size. The number of attention heads is 4, and the feed-forward network inside has a hidden size of 128. Now we stack 2 encoder layers using transformer encoder. Finally, we pass the input through the transformer. The output shape remains 10 by 1 by 32, the same as the input. Each token in the output now contains contextual information, meaning it has attended to other tokens in the sequence. This is a minimal working example of using transformers in PyTorch. Residual networks. Residual networks, or ResNets, were introduced to solve a big problem in deep learning. When networks become very deep, they are harder to train. The gradients shrink during backpropagation, and the model stops learning. This is called the vanishing gradient problem. To fix this, ResNet uses something called a residual block. Here's the key idea. Instead of learning a full transformation from input to output, the network only learns the difference, or the residual, between them. It does this by adding the input directly to the output of a few layers. This addition is called a skip connection or shortcut connection. It helps the gradient flow through the network and allows us to train much deeper models, like 50 or 101 layers. ResNet was a major breakthrough, and many modern architectures now use residual connections. Now let's look at how to implement a residual block in PyTorch. We start by importing PyTorch modules. Next, we define a custom class called Residual block, which inherits from neural network module. Inside the constructor, we define two convolutional layers. Each one uses 64 input and output channels, a kernel size of 3, and padding of 1 to preserve spatial dimensions. We also add batch normalization after each convolution. In the forward function, the input is first saved in a variable called residual. Then we apply the first convolution, followed by batch normalization and the ReLU activation. After that, we apply the second convolution and batch normalization again. Before applying ReLU, we add the saved input, or residual, back to the output using the plus equals operation. This is the skip connection. Finally, we return the ReLU of the summed output. At the end, we test the block using a dummy input tensor with one image, 64 channels, and a 32 by 32 resolution. The output shape is the same as the input, 1, 64, 32, 32. This is a minimal implementation of a residual block, and it's the core of how ResNet models are built. Recurrent neural networks, or RNNs, are designed to handle sequential data. Unlike feed-forward networks, where each input is processed independently, RNNs maintain a kind of memory of previous steps in the sequence. At each time step, an RNN takes in a new input, along with the output from the previous time step, which provides context. This cycle of information flow through time allows RNNs to remember and use information from earlier steps, making them great for tasks like language modeling, speech recognition, and time series forecasting. However, RNNs can suffer from vanishing gradients when trained on long sequences, which makes them difficult to train effectively on long-term dependencies. This led to the development of more advanced architectures like LSTMs and GRUs, which are designed to address this limitation. Now, let's look at a simple example of an RNN in PyTorch. We start by importing PyTorch modules. Next, we define a simple class, simpleRNN, that inherits from nn.module. In the constructor, we define the RNN layer using nn-RNN, where we specify the input size and hidden size. We also define a fully connected layer to map the hidden state to the output. In the forward function, we pass the input x through the RNN layer. The output of the RNN includes two values, the actual output and the hidden state. But we only need the output. We then take the last time step's output using out -1 and pass it through the fully connected layer to get our prediction. Finally, we test the RNN by creating a dummy input tensor of shape 5, 7, 10, which represents 5 sequences, each with 7 time steps and 10 features. We run the forward pass, and the output shape is 5, 1, which corresponds to 5 predictions. This is a basic RNN in PyTorch, suitable for sequential tasks. Debugging and visualization. Using TorchViz for graph visualization, TorchViz is a Python library that helps you visualize the internal computation graph of your PyTorch model. This graph shows how tensors flow through operations during the forward pass. Each node in the graph represents either a tensor or a function, and the arrows show the flow of computation, how inputs are transformed step by step. This is especially helpful for debugging. When you want to understand how data and gradients move through your model, you can detect disconnected layers, repeated computations, or wrong shapes in your graph. To use it, you import make.dot from the TorchViz library and pass in the model's output along with parameters. Now, let's look at the code example to see how it works in practice. We start by importing the required modules, including make.dot from TorchViz. We define a simple neural network called TinyNet with two fully connected layers. The first layer maps 4 inputs to 3 hidden units. The second layer maps the 3 outputs to a single prediction. We create a random input tensor with shape 1 by 4 and run it through the model. Then we call make.dot and pass in the output of the model, along with the model's named parameters. We render the graph to a file named tinygraph.png. This generates a visual diagram of the computation graph, which helps you debug how tensors and operations are connected inside your model. This method is especially useful in complex models like transformers, where tracing the flow manually is hard. Now let's take a look at the generated graph. At the very top, you see the learnable parameters of the model. These include the weight and bias tensors from the first and second linear layers. For example, fc1.weight has shape 3 by 4. That means it maps 4 input features to 3 outputs. Similarly, fc2.weight is shaped 1 by 3, mapping 3 features to a single output. Each parameter is connected to an accumulate grad node. That means gradients will be collected and stored there during the backward pass. As we move downward, we see operations like t-backward, which stands for the transpose operation used during matrix multiplication. Then there's add-backward, which is short for add matrix multiply. This is the operation performed by a linear layer. It combines the input, the weight matrix, and the bias term in the graph. There are 2 such add-backward nodes, one for the first layer and one for the second. At the very bottom, highlighted in green, is the final output tensor. Its shape is 1 by 1, matching the expected output of the model. So what does this graph show us? It shows the full chain of operations, from parameters to intermediate computations to the final output. This allows you to verify that all layers are connected properly and that gradients will flow as expected when you call backward. If something is disconnected, or if a tensor is not used in computation, it won't show up in the graph, making TorchViz a powerful debugging tool for PyTorch models. TensorBoard is a visualization tool originally built for TensorFlow, but PyTorch supports it too through the Summary Writer class. To use it, first import Summary Writer from torch.utils.tensorboard. You can log scalar values like training loss or validation accuracy. This helps you track how the model is improving over time. You can also log other types of data, such as the model's computation graph, images, or histograms of weights. All logs are written to a folder, usually called runs. To view the logs, open a terminal and run TensorBoard --logdir equals runs. Then open the provided link in your browser. This gives you a live dashboard to monitor your model's progress. Let's walk through this code step by step. We start by importing Summary Writer from torch.utils.tensorboard. We also import torch and torch.nn. We create a simple linear model with 10 input features and 1 output. We generate some random input and target data for demonstration purposes. We use mean squared error as the loss function. Then, we create a Summary Writer object. This is responsible for saving all logs into the runs folder. Next, we enter a training loop for 5 epochs. Inside the loop, we make predictions using the model. Then we calculate the loss by comparing predictions with the targets. To log the loss, we call addScalar. We pass in the tag loss/train, the loss value, and the current epoch. On the first epoch only, we also log the model graph using addGraph. This lets you view the structure of the model inside TensorBoard. Finally, we close the writer at the end. Once this script is run, you can view the results using the command TensorBoard-logdir equals runs. This opens a web interface where you can track the loss over epochs and explore the model's internal structure. This kind of visualization is very helpful when debugging models or explaining training behavior to your team. Printing gradients and model internals. To debug a model in PyTorch, you often need to inspect its internals. The most direct way is to print the gradients. After calling backward, every parameter has a .grad attribute. This tells you how the loss is affecting each weight. You can also inspect the model's weights and biases using .parameters or .named parameters. To go deeper, you can register hooks on layers. Hooks let you print or record the input and output of a layer during the forward or backward pass. This is very useful for spotting issues like vanishing gradients, exploding values, or incorrect shapes. Being able to inspect gradients and activations is a key part of debugging and understanding deep models. Let's walk through the code for printing gradients and internal activations. We start by creating a small model with 2 linear layers and a ReLU activation. We create some random input and target data. Then we run the forward pass and compute the loss using mean squared error. After that, we call backward to perform backpropagation. To inspect gradients, we loop through all named parameters in the model. We print the name and the .grad tensor for each one. This shows how each parameter is being updated based on the loss. Next, we demonstrate how to inspect activations using forward hooks. We define a function called printActivation that returns a hook. Each hook receives the input and output of a layer during the forward pass. We register this hook on FC1, ReLU, and FC2. Then we run the model forward again. This triggers the hooks and prints the activations of each layer. This is extremely useful when your model is not learning or behaving unexpectedly. By printing gradients and activations, you get a window into what the network is really doing inside.
Thanks for watching.